Hello students, a very warm welcome. Today we'll be covering lecture 2 of periodic properties, in which we'll be talking about defining elements by block, right? We know that there are 4 blocks S, P, D and F, right? Then we'll be talking about effective nuclear charge and shielding effect. So let's get started. The first slide coming your way, right? It says 4 spins, right? What if there were 4 spins to the electrons that could enter the subshells, guys, right? So this is hypothetical, of course, right? This does not happen, right? There are only 2 spins, right? That's what we know scientifically, right? There are only 2 spins. This is a hypothetical case. What if this happens, right? So now we knew that in the s orbital, right, earlier, right, when there were only 2 spins, 2 electrons could go max, right? So there could be 1 electron, 2 electron max, right? Now that it has 4 spins, 4 electrons can go 1, 2, 3, 4, right? Okay. Similarly, if you are talking about the p subshell, earlier in the p subshell, 1, 2, 3, 4, 5, 6, maximum of 6 electron could go. Now if you see, there could be, right, there could be 6 more electrons that could go in it, right? So if we write the electronic configuration of chromium in this hypothetical case, chromium we know has atomic number 24, right? So it will be 1s4 now, right? 4 electrons can go in it, right? First shell does not have any p subshell, right? Then there will be 2s4, right? Then there will be 2p6, right? So will it be p6? No, right? Again, this will be 12 because there are 4 spins, right? Instead of 2 spins earlier, right? So it will double, right? So it will become 12. So now we have got 16 electrons covered, right? Now, in fact, 20 electrons covered we have right now, right? So now the remaining 4 electrons will simply go into the third s subshell, right? So it will become 3s4, right? So if you're talking about the period we know will be the third period, right? It's the final, the outermost shell in which the electron goes. So this is the third s shell. So this is the third period, right? Because it's the third shell that gets filled, right? The final shell that gets filled, the third shell, right? And apart from that, guys, what will be the group number? Guys, now the group number would be, if there was now the new s block, right? Now the new s block, earlier the s block was the first group and the second group, right? This was the s block in the periodic table, if you remember from the last class. Now because there could be 4 electrons in this hypothetical situation, guys, right, there can be this third and fourth electron going into the subshell, and we have 4 electrons in the s subshell, guys. So this will now be, this entire will be now the s block, right? So this is s4, right? So this will be the first electron of this one goes into s1, then s2, then s3, then s4, right? So basically this will be the 4th group, right? If it was 3s2, for example, it would have come over here in the second group. If it was 3s3, it would have come in the third group. If it was 3s4, it came in the 4th group, right? If it was 3s1, of course, it would have gone into the first group, right? So the s block has enlarged, right? So will the p block, d block, f block enlarge, right? So if you notice, the periodic table will become wider and smaller, right? Do you understand this, guys? Right? I hope you've understood this, guys. And I'll move on to the next question. So the answer to the previous question, of course, becomes third period and 4th group, right? Next, similarity in chemical properties of the atoms of elements in a group of the periodic table is most closely related to, guys, we studied this very well in the last class, right? Mendeleev made a leap. He said atomic masses, and then Moseley was finally able to draw a more stronger correlation with the atomic numbers. right? So the correct answer to this is atomic numbers. Don't get confused with the number of valence electrons. No, right? Number of valence electrons does not define the group, right? It's the atomic numbers. The atomic numbers is what the periodic table, the modern periodic table is based on. I hope you've understood this, guys. Option A is the right answer. I'll move on. Classification based on electronic configuration. So the first thing that we'll be talking about is the S block, right? S block elements, right? S block element is one in which the final, right, the last electron enters the s orbital, right? For example, if you're talking about hydrogen, this is 1s1, right? This is lithium, this is 1s2, 2s1, right? This is 1s2, 2s1, 2p6, 2s2, 2p6 and 3s1, right? Like that, right? So all of them will have, so this will be 4s1, the final shell will go into the fourth subshell. This will then be 5s1, this will be 6s1, this will be 7s1, right? I hope you've understood this, guys. So the last electron enters into the s orbital. Those are s block elements, right? Their general electronic configuration is ns 1 to 2, right? Alkali metals from, so hydrogen, this first group, right? The elements in the first group are called alkali metals, except hydrogen, right? This lithium, sodium, potassium, rubidium, cesium, francium, all these are alkali metals, right? And the second group is called the alkaline earth metal groups, guys, right? So we have beryllium, but beryllium is not called an alkaline earth metal. It shows properties which are not very similar to the remaining elements of this second group, right? But magnesium, calcium, strontium, barium and radium, these are, guys, these are the alkaline earth metals, right? So alkali metals, guys, have valency 1, right? These are from lithium to francium, right? And when the property of these alkali metals, guys, is that when they react with water, right, they react explosively. A lot of energy is released, right? So almost fire is produced, right? So lithium does not produce fire, right? It does not have that much of a it's not that much of an exothermic reaction, but after that, sodium, potassium, everything, right, they catch fire when water is poured on them, right? So an alkali metal, when reacts with water, it forms MOH, hydroxide, plus H2 gas is released, right? And a lot of heat is released, right? I hope you've understood this, guys. Alkaline earth metals are, guys, magnesium to radium, right? So beryllium, although it's in the second group, it's not considered a part of these, right? In fact, hydrogen can be a metal, it can be a non-metal as well, right? So it's we don't say that it's an alkali metals in fact, right? About alkaline earth metals, right? These are magnesium to radium, right? Radium is of course radioactive, right? So we won't talk about that, but valency, if you see, is 2, right? 2, right? I hope you've understood this, guys. About reactive metals with low ionization energies, guys. So this would be, if you notice, this beryllium, if we talk about, would be 2s2, this will be 3s2, this will be 4s2, right? Like that. Reactive metals with low ionization energy. These are reactive metals with low ionization energy. What ionization energy means, guys, is ionization energy is the amount of energy required to remove the most loosely bound electron, right? So the most loosely bound electron will definitely be in the outer shell, right? The outermost shell, right? So to remove that outermost shell electron, the most loosely bound electron, right, whatever the amount of energy required is, guys, that will be your ionization energy. So the lower the ionization energy, the easier it is to form a cation, right? So this is ionization energy. So both alkali metals and alkaline earth metals, they have low ionization energy. They form ions very easily, especially if they are placed in a aqueous solution, right? And hence they are very reactive, right? Because these cations or anions, in this case cations of course, these are intermediates, right? These are intermediates, they are very reactive, so they get formed because of low ionization energy, and the moment they are formed they would react, right, and form something else. So that's why these sodium, potassium, magnesium, calcium, these are very reactive, guys, right? A lot of heat is released in the process of their reaction most of the times, right? I hope you've understood this, guys. I'll move on to the next thing and talk about the p block element. This is the p block element: boron family, carbon family, nitrogen family, oxygen family, fluorine family, then the halogens, right? Then the noble gases, right? These are called p block elements because the last electron, the final electron, enters into the p subshell, right? So this is the boron family: boron, aluminium, gallium, right? Indium. This is thallium perhaps. These 5 you have to remember over here: carbon, silicon, germanium, tin, and lead. Very important, right? So lead and tin come in the carbon group, right? Carbon, silicon you obviously have to remember because, right? And perhaps, right? So it's very easy. So from over here there is a difference of 8, then again 8, then 36, then 18, then again 18, then 32, then again 32, right? So if you're starting with, let's say, boron family, the boron has atomic number 5, so aluminium will have atomic number 13, right? 8 is the difference, then 31, because again 18 is the difference, right? Then it will be again 18, so indium will be 49, right? So boron, aluminium, gallium, indium, thallium, perhaps you can remember. Carbon, silicon, definitely germanium, tin, lead, right? Nitrogen, phosphorus, arsenic, antimony, bismuth, all 5 are very important. Try to remember their atomic numbers, right? And if there are any exceptions related to them, you have to remember them, right? Nitrogen family, guys, you might remember from the last class, they are pnictogens. Oxygen family are chalcogens, right? These 17 group elements, right? These are halogens: fluorine, chlorine, bromine, iodine, acetylene, right? These are halogens, right? And these group 18 elements are noble gases, right? I hope you remember all this, guys. So helium, neon, argon, xenon, krypton, right? Krypton, xenon, radon, right? These are very important, right? These 1, 2, 3, 4, 5, 6 till radon are important, right? And try to remember, especially try to remember the atomic numbers of these, guys, because if ever you have to find the position of an element in a periodic table, right? If you just remember because this will be, if you know, this will be 1s, this helium definitely is 1s2, right? So this is the p block does not get filled, right? But but it's still included in group 18 because it's a noble gas. So this is sort of an exception over here, but this is still a noble gas, so you must remember that this is 1s2. That's sort of an exception, so let it be over here. Then this neon, this is 2p6, this is 3p6, right? The final shell, right? The final shell configuration, right? But obviously there will be something before that. Then this is 4p6, right? Then this is 5p6, and you should remember the atomic numbers: 2, 10, 18, 36, 54, 86, right? 2, 8, 18, 18, 32, 32, right? Like that. 2, 8, 8, 18, 18, 32, 32, right? So if you begin with over here, the next difference will be 8, then 8, then 18, then 18, then 32, then 32, right? So if you know helium, right, next is neon, right? So you'll add 8 to that. I hope you've understood this, guys. So these are the p block elements. We've seen that in detail in the last class as well. I've given you quite a bit of a reminder, right? Of course, halogen family you can very easily remember, right? A lot of elements, right? Very reactive, so they occur in a lot of reactions: fluorine, bromine, iodine, acetylene, right? Tennessine is not important, right? Please try to remember all these things, right? I hope you've understood this, guys, and I'll move on. So in p block elements, guys, last electron enters into the p orbital. General valence shell electronic configuration, if you see, for the 13th one, which is the boron family, right, group 13, which is boron family. This is boron family, and it all starts from here. This is boron family, this is carbon family, this is nitrogen, this is oxygen family, this is the halogen family, right, and then this is noble gases, right? Okay, so this is ns2 gets filled, then np1, this is np2, np3, np4, n5, p5, np6, guys, right? Of course, guys, metallic properties increase as we go down the group, right? In case of p block elements especially. So what happens is, guys, the ionization energy becomes low, right? So the tendency to form a cation becomes high. So but basically metallic character is the tendency to form, it's defined. So non-metals are those which can easily give out and which can easily take an electron, and metals are those which can easily give out an electron and become positively charged, right, and ionize. So if you go further away from the nucleus, right, the nuclear pull keeps on decreasing, right, hence down the group the metallic nature increases, right? I hope you've understood this, guys. Next up, d block elements, guys. D block elements we've talked about in detail, right? So d block elements start from scandium, right? So scandium, guys, if you write the configuration of scandium, which is 21, it will be 1s2, 2s2, 2p6, right? Then it will be 3s2, right? Then 3p6, right? So how much have we got covered? 4, 10, 12, 18, right? Now it will be 4s2 and 3d1, right? Because if you remember from the last class, the nth s orbital has the lowest energy, followed by n-1 dth orbital, right? n-1th d orbital, then n-2 th f orbital, then the nth p orbital, guys, right? So this d block, the final electron goes into the d subshell, right? After this s subshell is filled, only then does it go to the d subshell, guys, right? So the final electron goes to the d subshell. So for all of them, right? So for all of them, right? All of them, the final electron goes into the d subshell, guys. One more thing you should remember over here, that although lanthanum and actinium, right, the lanthanide and the actinide series, after them they are named, right? So lanthanum and actinium, guys, the valence, the final electron actually goes into the d orbital instead of the f orbital, because the transition energy between d and f is very low. So you might never know that it's whether it's lying in the d orbital or it's lying in the f orbital. We are talking about just one electron in both the cases, guys, in case of actinium and lanthanum, right? That is 50, for example 57 is the atomic number of lanthanum. So we know over there that it can go into the d orbital, the final electron, or into the f orbital. It should have gone into the f orbital ideally, right? But there is just one electron. The f orbital has a larger energy, so you can understand like this. So it will just say that, you know, just one electron, I might just as well go in the d orbital instead of the f orbital, right? And it will occupy much more of a space. So that will be, you know, to keep that up, to keep that system, it will be a lot more energy. So transition energy is very, very comparable in that case, right? Between the d subshell and the f subshell in that number. For example, in lanthanum and actinium, that is why sometimes they are said that they are in the d block, sometimes they are said in the f block, but definitely the probability of them going in, the final electron going into the d subshell is higher than it going to the f subshell, right? I hope you've understood this, guys. So this was about d block elements, guys. So about d block elements, guys, I told you what all to remember, right? A lot many things to remember. So definitely till 30 you should remember everything, right? Scandium, titanium, manganium, chromium, manganese, iron, cobalt, nickel, copper, zinc, right? You should remember that, right? After that, definitely chromium is followed by molybdenum, tungsten, right? These three are important. Molybdenum, tungsten is used as a catalyst in a lot of places, right? Molybdenum is also has a lot of uses. so that this is very very important, right? Then iron, right? Iron, and then ruthenium is what follows iron, so just you should remember, because iron in itself is very very important. Then this is cobalt, right? Nickel, palladium, platinum, very very important. Platinum, palladium are used as catalysts in a lot of cases, right? So it occurs very frequently in your chemistry, so you must remember the atomic numbers of nickel, palladium, platinum, right? And their properties. Copper, silver, gold, right? You remember from this last class, right? These are coinage metals, right? Or so these three you must remember: copper, silver and gold, right? They come in the same group. So if you remember copper 29, then you can add 18 and then 32, right? You get, because if you see the periodic table, if you see it starts from over, so they, for example, if I'm talking about the 18th group, it will be helium over here, then it will be neon over here. There is a difference of guys 8, right? Now if we follow it with argon, guys, right, if we follow it with argon, so helium, neon and argon, so the difference is of 8, then it's of 8, then it will be of 18, right? Argon is, then the next one, which is krypton, would be 36, right? So this is 2, this is 10, this is 18, then the next krypton will be 36, guys, right? So this is a first period, second period, third period, fourth period. So this fourth period you should remember for D block very very well, right? Till fourth period you should remember the periodic table at your tips. After that, you know, certain elements you can remember, right? The noble gases, you should definitely remember all of them, right? Because noble gases will give you a yardstick to determine where will some element with some atomic number lie in the periodic table, in which group and in which period, right? So once you know this, you will be able to figure that out, right? Apart from that, guys, this iridium is important, right? Iridium has a lot of uses, that is important. And talking about zinc, right? This group, right? In this group, zinc, cadmium, mercury, important, right? Copper, nickel also comes over there, so you can remember that, right? And of course, these are called transition elements. The D block elements are called transition metals or transition elements, right? They are more metallic than non-metallic. They have a tendency for showing metallic character, right? So I hope you've understood, guys. So we talked about metallic character also, right? They are sonorous, they are lustrous, right? All those things, right? But chemically, if you define metallic character, it will be the lowest ionization energy, the easier, I mean, the lower the ionization energy is, the more the metallic character will be, guys. All right. I hope you've understood this, guys. And I'll move on. The last electron enters into the F block in case of F block elements, guys. So it starts with it's the lanthanide series and the actinide series, right? When we are talking about the F block elements, right? Lanthanum and actinium, guys, these two, right? The final electron actually goes into the D subshell, right? For these two, right? But for all of them, these, right? So 58 to 71 and 90 to 103, you can count 14, right? 14 is the number of electrons that can go into the F subshell, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So from cerium to lutetium, right? And thorium to lawrencium, right? These go into the F block, right? These do not go into the F block. The final shell does not go to the F block. These are mentioned over here, guys, because these are lanthanide and actinide series. So what we do is we remove that entire series, right, which would go over there, and put it at the bottom, right, so that it's more organized, right? Organization is all what we wanted from the periodic table, right? Because there were so many things coming up, so many elements that were getting discovered, we wanted some sort of an organization, and that's why we discovered we made, in fact, a periodic table, right? I hope you've understood, guys. Just organize things, right? Now talking about some exceptions, guys. So if you're talking about chromium, copper, niobium, molybdenum, rubidium, so if you're talking about, let's say, expected, right, and then we say reality over here, right? What's the reality? What's the configuration, right? Some exceptions in electronic configuration. So we know exceptions in organic chemistry are very prominent, right? And this exceptions, as I told you in the last class, we made all efforts to organize things in a periodic table, right? But there were certain properties, right? Those are different elements that we organized according to their atomic numbers, right? But they have different properties, right? They have, you know, their journey from the starting, from how it was made, right? So initially, if you remember, in the star burst, right, the hydrogen was made, then helium was made, and all the elements were made. So they've made different journeys, right? So as to, if I try to personify them a lot, then in that case, guys, what we have is, we definitely have exceptions because we've tried to organize them into one mold, right? But there will be certain properties that will be different, right? So we'll have to talk about those differences separately, and hence we have a lot of exceptions, guys, right? To address those differences, right? And it's not that these are exceptions for some random, there is proper scientific reason for these exceptions, right? And we'll talk about them gradually, right? For example, if you talk about these exceptions, if you talk about the electronic configuration of chromium, copper, niobium, molybdenum, ruthenium, rhodium, right, palladium, lanthanum, cesium, right, all of them if you talk about, right? So guys, what we have over here is this would be what you'd expect, right? So this is 4s2 3d4, right? And then copper should be 4s2 3d9, right? 29. So if you go about writing, for example, chromium, right, 24, you would say 1s2, 2s2 gets filled, right? Then of course 2p6 will get filled, so we have 10 electrons covered. Then 3s2, then 3p6, so 18 electrons covered. Then 4s2, and of course now there is no F shell, so that means a D shell will get filled, and we have a 3D shell, so it should be 3d4, right? And when you do that, you'll get a 0 mark, right? Why is that, guys? The reality of this would be, I mean, this is the expected thing, right? This is what you'll expect, but the reality is, what will happen is, half filled subshells and full filled subshells are much more stable than any other electronic configuration, right? I mean, I'm talking about the valence electron, of course. The previous shells will definitely be filled. For example, till here, this is argon, right? So up to argon, everything is fixed, right? Because it's a noble gas. We're talking about that, right? So this is how very easily you can write configurations as well, starting with a noble gas and then proceeding forward, right? All these are noble gases, argon, krypton, xenon, right? So the reality, for example, of chromium would be argon, right, and 4s1 3d5, right? We know that in S subshell there are 2 electrons maximum possible, and in D subshell there are 10 electrons maximum possible. The half filled number would be 1 and 5 respectively, right? So instead of one fulfilled, which was 4s2, right, and one, you know, just had 4 electrons, neither full neither half, right, what we did was we settled for a 4s1 3d5, right? Because this exchange energy for one electron from going from 4s to 3d will be much less required than in comparison to what the stability that is obtained, right? So the net energy exchange would be lower. I mean, so a more stable configuration will be this, right? So for example, if you talk about copper is argon. The reality of copper is argon, right? 4s1 3d10, right? Now we have one half filled and one full filled, right? If we talk about, for example, niobium, right? So this actually becomes krypton and then 5s1, guys, and 4d4, right? This is much more probable than that, right? Then if we talk about molybdenum, guys, this becomes krypton and then it becomes 5s2 5s1 4d5, right? Guys, if we talk about niobium, which has Z is equal to 41, right, between 5s1 and 4d1, right, what happens is, guys, it becomes 4d4 for a certain reason, because again the energy exchange and the final energy that is obtained, right, the delta G is still negative, right? So that is why you can remember this as an exception, guys. Again, an exception with an exception, that this niobium would show 5s1 and 4d4 instead of this, right? If we talk about molybdenum, guys, which we have talked about here, it will be simply the half filled shell thing over here, right? Then over here again, guys, if we talk about this is chromium 5s1 4d7, guys. 5s subshell half filled 5 we are talking about specifically is much more stable than the full filled subshell S, right? If we talk about this, guys, this again becomes 5s1 and then 4d8, guys, right? 5s1 4d8, this becomes 5s1 4d9, guys. You should remember this, right? Then this palladium, guys, these are exceptions, guys, all right? Then if you talk about this becomes this silver, it becomes 5s1 4d10, right? Silver, gold and all, you must remember, for example, guys, they are called noble metals, right? Because they are very, very less reactive, right? If we talk about lanthanum, guys, so lanthanum, what happens is, I've told you before, the reason for lanthanum not having this 4f1 configuration, guys, is that it becomes 6s2 and 5d1 instead, right? Instead of going into 4f, which it should have ideally gone into, it goes into 5d, right? Because I've spoken about, I've told you about the transition energy and everything, so that's very, very important. I hope you've understood this, guys. Then there is cerium, right? So this is the electronic configuration that you would expect, but it becomes 6s1 and 4f1, guys, right? So you must remember all this, right? So these are the exceptions that you must remember, right? Now, how to locate a random atomic number mentioned in the group and the period? Guys, what you should remember over here is, this is helium, right? This is neon, this is argon, this is krypton, and this is xenon, right? And then there is radon and all. You should remember till at least here, right? And these over here go as the lanthanide and the actinide series, right? This is lanthanum, right? This is actinium, right? This is what we have. Then from what we have over here, guys, is Ce to deuterium, right? Cerium to deuterium, and over here this is lawrencium, right? So this is actinide series, this is lanthanide series. So these two actually go into these are not f block elements exactly. They come in, the final shell goes into the final electron goes into the d subshell. Ideally, more probably the probability of that doing that is high, right? But this is definitely f block, right? These 14 elements are f block and these 14 elements are f block, right? So now if you have to locate z is equal to 45, guys, so this is 2, right? This is 10, the atomic numbers. This is 18, right? Then this is 36 and this is 54, right? And then of course radon will be what? It will be 86, right? If you add 32, right? So this is what we have. Now if you have to figure out 45, now 45 you can see is 36 plus 9, right? Or you could have gone 54 minus 9, right? Anything you could have done over here. Now if I go 36 plus 9, guys, what we'll do over here is, this is 36, right? This is 36, guys. This will be 37. This will be, I'll change the color of the pen because it's not very visible, right? This will be 37. This will be 38. This will be 39, 40, 41, 42, 43, 44, 45. Although there is this break in the periodic table, right? But nothing is changing. I mean, the lanthanide and the actinide series is this, right? The F block is this basically, right? So it goes over here completely, right? It gets picked up from these over here and over here only, not from over here, right? So I hope you've understood this, guys. So 45th is over here. So if you notice, what will be the period number? This is the first, this is the second, this is the third, the fourth, this is the fifth. So the period number will be 5th, right? This is 5th period. And what will be the group number, guys? This is the first group, second group, third, fourth, fifth, sixth, seventh, eighth, ninth, right? So ninth group. So we've located the element, right? Now if we go 54 minus 9, guys, so 54, this will be 53, 52, 51, 50, 49, 48, 47, 46, 45. Again we'll get the same number and we can locate it again, right? Now if we talk about the second one, guys, I'll just delete it. Talk about the second one now, which is 73. All right, so this is 73, right? The second one is 73. We know helium, neon, argon, krypton, xenon, right? Radon, right? This is 2, this is, right, this is 10, this is the atomic numbers I'm talking about, this is 18, this is 36, this is 54, and this is 86, right? So guys, if you know, neon is 2p6, right? The valence shell configuration, the final, because p block element again, so 2p6, the final electron goes into 2p shell, so 2p subshell, so this will be 2p6, this will be 3p6, this will be 4p6, this will be 5p6, this will be 6p6, right? So guys, this will be the p block, right? Till over here will be the p block, so means 85, 84, 83, 82, 81, this is the p block, right? Then this will be 80, 80, 79, right? This is 86, 85, 84, 83, 82, 81, 80, 80, 79. Then now the D block has started, right? D block has already started, right? These 6 have gone in the P block. This is 80, 79, 78, 77, 76, 75, 73, right? So 73 we have obtained over here. It's definitely in the D block, right? Why will it be in the D block? Because if you notice, this is 6p6, right? This radon is 6p6, right? The final shell, right? So before that, if you notice, guys, if we start from 6s2, right? This is the order it gets filled, 6s2, then 4f14 will get filled, right? 14 electrons, right? And then it will be what? It will be the, before just cp6, 6p6, what would get filled, guys, is 5d10, right? So we are filling 5d10 over here, right? So 5d10 would go till 70 over here, right? So this is 73, this is 72, 71, 70, right? And over here, if you notice, guys, if you notice, all of the remaining ones, guys, from over here, if you bring it to over here, these will be the actinium, the lanthanide and the actinide series, guys, right? So I hope you understand this. So this 73, guys, comes over here, right? It comes over here. In which period it is? It is in first, second, third, fourth, fifth, sixth, right? Sixth period, definitely. Sixth period, 6 is the final shell that is getting filled, and the fourth and the which period? First, second, third, fourth, fifth, sixth, right? I hope you've understood this, guys. This periodic table might not be properly made, but I hope you've understood this, how it is done and how it is not done, right? So these two examples, if you try it a couple of times, you'll be able to understand it and do it according to yourself, right? So these configurations is what you must remember. Or what you can do perhaps is, guys, you can say that no, I won't like to start from here. What I'd like to do is, I would like to start from here. So this is zinc, right? So zinc is 30, right? Then 30, then you'll say you know that this is 30, then what I'll go for is this is the next one, because this difference is 8, then 8, then, right, then again 18, 18, like that, 18, 18, 32, 32, like this, right? So if you go from over here to over here, the difference would be 18, so this would be 48, right? And this would be what? This will be 80, right? This will be 80 if you add 32, then this would be 116, right? So you can either go from over here or go from over here and then figure out the elements, right? So you can actually start from anywhere, right? Generally starting with noble gases works a lot, or starting from over here if you're talking about D block elements particularly, right? Or closer to them, then this could also work, right? You can start from over here, right? I hope you've understood, although you can start from anywhere. I'll move on. All right, so for this particular question, guys, if you notice option C, right, if you add 8 to this, right, then of course the next time you won't be able to add 8, right? So what we do is we do 2, 8, 8, right? So the K shell gets filled with 2 electrons, L shell, the second shell gets filled with 8 electron, then the third shell again gets filled with 8 electron, then 18, then 18, then 32, then 32, right? It gets filled like this, right? So first this will be 2 and then 6, right? So this is basically, this is what? This is oxygen, right? 2 and 6, right? And after that, the next one will be 16. That's true, because we added 8. Now we'll have to add, this time what we'll have to do is we'll have to add, because till 10 then 18, right? Then 18, next we'll have to add 18, right? So this time the jump has to be 18, so it has to go till 34. So option C is definitely wrong. So I mean, in this case they're asking which do not belong to the same group, it will be option C. If you see for option A, this is after 2, right, till 10 it will be over here, right? Then after that, I mean, there will be a 8 jump, right? And then after that there will be again an 8 jump. So 3, 11, 19, and then you will add an 18, so it will give you 37. So this is, I mean, this is not the correct answer, definitely, right? And so aren't B and D. So which do not belong to the same group, it will be option C. Option C is the right answer. I hope you've understood this, guys. All right, I'll move on. In the long form of the periodic table, guys, so this is again very simple question. So what you have to do over here is, this is 5s2 5p4, so definitely the fifth period. A and D are eliminated, right? Now once you have 5s2 going into this group, right, 5s2 and then 5p4, right? So 5s2 means that it will be the first S, then the second S group, right? And then if you're talking about the period, guys, so the, I mean, the group you're talking about, right? So if you notice, groups 13, 14, 15, 16, 17 and 18 are the P block, right? And in the P block, 4 electrons are filled, so this will be first, second, third, fourth, right? So we'll get 16 as our group. So group 16 and period 5, option C will be the right answer, guys. All right, I'll move on. Next is effective nuclear charge, guys. So effective nuclear charge, basically the concept says that although the nuclear will have a certain charge, right? I mean, the nuclear will have certain charge, right? Outer electrons are attracted towards the nucleus by a nuclear charge, right? But this nuclear charge will get reduced because of the repulsion of inner electrons. So the outer electrons, right, as you go further and further away, I mean the first shell, if you're talking about, won't experience any change in nuclear charge. I mean, there will be no electrons shielding it, basically, right? There will be no electrons shielding the outer electrons. But if you're talking about these outer electrons, I mean, if you go beyond the first shell, right, then these inner shell electrons, right, all the inner shell electrons will be shielding these outer shell electrons, right? In fact, because of the inner shell electrons, they will also face a repulsion, right? So they will move further away from the nucleus, so nucleus won't attract them as much as they do the inner electrons, right? So hence the effective nuclear charge that these outer electrons will experience will be lesser than the inner electrons, guys, right? So if this is the nucleus and this is the first subshell, second subshell, third subshell, right? So this first shell will experience the entire nuclear charge. This will experience something less, right? This will experience further less, the electrons over here, and as we go further it will experience lesser effective nuclear charge, right? So this is the concept of effective nuclear charge, right? So screening effect is basically the decrease in the force of attraction exerted by the nucleus. So basically the effective nuclear charge becomes lesser and lesser as we move further away from the nucleus. As the shell number increases, the attraction force from the nucleus is reduced, right, due to the inner electrons, right? So for example, if you are sitting in a concert, right, if you, let's say, attend a A.R. Rahman concert and you are sitting over there, right, the first rows will hear clearer voices, right? But as you go back into the rows, right, the voices become that much less, right, intensified. If he's singing from the front, right, and there is no proper music system, then of course, right, the people sitting in the back, the voice they would hear, right, would not be as clear as the voice that people hear in the front, right? So I hope you understood, right? So Z effective, right, the effective nuclear charge, right, Z effective, the effective nuclear charge is Z, which is the atomic number minus the screening constant sigma. So where sigma is the screening constant, guys, right? Further guys, variation of effective charge. So for example guys, if you're talking about effective nuclear charge on the outermost electrons guys, then the atomic number of lithium is Z, right? But the Z effective that they will encounter, right, or they'll face is only 1.28. I'm talking about the outermost electrons. In case of beryllium, the atomic number is 4, right? So they should ideally experience a charge of 4, right? Effective nuclear charge of 4 because there are 4 protons, but they experience only 1.91. For boron it's 5, right? They experience 2.42, right? And so forth, right? So this is basically period 2, right? This is period 2, right? And as you can see, as you move across a period, right, Z effective increases, right? Try to think why it increases, and I'll answer that in the next class, right? It has something to do with addition of more electrons, addition of more protons, but the shells don't get increased, right? So I hope you understood the logic over here and you can identify the reason over here. So across a period in general, right, in general, there will be exceptions, right? As I've told you, in general Z effective increases, right? Please take a screenshot of this, right, and read these Slater rules, right? Slater's rules. Read these Slater's rules, guys, right? Read all the 5 rules. We'll be able to understand them, although we'll be covering them in the next class as well, right? So in this class, we've talked about periodic properties much more in detail right now. We've talked about the SPDF blocks, right? We've talked about Z effective. We've talked about screening effect, at least introduced to them, few to them, right? And we've talked about locating elements in a period, right? We've talked about atomic number 45, for example, atomic number 73. So you should be able to do all that stuff, right? So I mean, the more you practice, the more you'll get attuned to that, right? Look at the periodic table as much as possible. Have it in your room, taped to your wall, right? It will help you a lot, and you will be able to understand the periodic table. There are certain elements that you can remember very well. For example, if you know, just form your own methodologies of remembering them. Up till 30, you definitely have to remember, perhaps up to 36, right? 36 till which is krypton, you should remember everything, right? After that, you can remember certain things, right? For example, below copper come silver and gold, right? So those coinage metals come one below the other, right? Copper, silver, gold, right? Then about tungsten, which comes in the same group as chromium does, right? So tungsten is again very important. Molybdenum is just before that, so again that is important. Then below zinc, whatever comes, that is very important, right? All the noble gases, it should be at your fingertips, right? So very easy. Helium, right? Helium is 1s2, right? The 2p orbital does not get start getting filled yet, but still it's kept in the p block, right, at the rightmost corner, right? So p block elements, so neon, then I mean the second period, and group 18, which is the noble gas, right? Helium, neon, then it would be argon, krypton, xenon, radon, right? So you should remember all of that, right? What are the elements below zinc? You can remember it. It can be a good starting point for locating the elements, right? And then the period, right? The period, you know, when the period is the outermost shell that get filled, right? For example, if the 5th shell is getting filled at the last, that will be your period number. And the group number would be, you know, if they are lying in the p block element, if the p block elements are getting filled at the last, I mean if the p subshell is getting filled at the last, they will be lying in the p block part, which is group 13 to 18, right? So once you know, for example, if there are 3 p subshells that are getting filled in the p 3 electrons finally that go into the final subshell, right, which is the p subshell, for example, right? Then you'll say that 1 2 3, okay, so 13 14 15, it will be the 15th group, right? Similarly, group 3 to 12 is the d block, right? And similarly you can figure out for the F block as well, right? So F block are the lanthanide and the actinide series. Lanthanide and lanthanum and actinum don't actually come in the lanthanide and the actinide series, right? The d orbital gets filled first, right? But they'll definitely come in the F block, right? Both lanthanum and actinium will come in the F block. 58 to 71 is the lanthanide series, right? I hope you remember that, guys. So 14 electron gets filled in the F block, right? So 58 to 71 is 14 elements basically, right? So from cerium till lutetium, right, and till lawrencium in case of actinide series also, guys, right? So I hope you remember all these facts, right? And I'll see you in the next lecture. Where we'll be delving further into periodic properties. We'll be talking about atomic radius, ionic radius, covalent radius, right, van der Waals radius, and all of that stuff. How atomic radius varies across a group, across a period, right? We'll be delving further into the properties, right? We'll be talking about bond length, bond strength, and everything, right? So please stay tuned for that, and I'll see you the next time around. Thank you.